Let us look at comparison test 3. This test is also called the ratio test or also as the Lambert ratio test. Now, first question to ask is, why do we require comparison test 3 when we already have 1 and 2? Now, remember necessary condition u sub n going to 0 is too weak to decide convergence. Comparison test 1 and 2 require guessing a good comparison series, which is not always obvious. So we require a test that looks only at the given series and detects how fast the terms shrink. Here, it is still called the comparison test, mainly because the comparison is with a geometric series which is implicit. That means we actually don't write down the corresponding geometric series. Why geometric series? Because when the common ratio r is between 0 and 1, a geometric series converges. And when r is greater than or equal to 1, geometric series diverges. We have seen this before. Now, in a geometric sequence, u sub n plus 1 is equal to r times u sub n. So, we have r is equal to u sub n plus 1 by u sub n, a ratio of two consecutive terms. So, we figure out whether the given series behaves like a geometric series asymptotically. What does asymptotically mean? It means for sufficiently large n. So if it does, we can implicitly compare and figure out the convergence divergence of the series. So let sequence of terms u sub n be a sequence with u sub n greater than 0 for all sufficiently large n. Let L be equal to the limit as n goes to infinity of the ratio of two successive terms. If the limit exists, then we have different cases. If this L is less than 1, implies there exists a number R between the limit and 1 and an index M such that u sub n plus 1 by u sub n, the ratio of successive terms, is less than or equal to R for all n greater than or equal to M. Since the terms are eventually dominated by a geometric sequence of ratio r less than 1 and the series converges. So if the limit as n goes to infinity of this ratio is less than 1, then we can say the series converges. Now, if the limit is greater than 1, then there exists r greater than 1 and m such that the ratio of the successive terms is greater than or equal to r, which is in turn greater than 1 for all n greater than or equal to m. So, which implies in general u sub n plus a is greater than or equal to u sub n times r to the power of k. So, the terms do not tend to 0, which means the necessary condition itself is not satisfied. And hence the series diverges. Now, if L is equal to 1, this only tells us that the decay is slower than exponential. For example, if we look at this series 1 by n, if we take the limit as n goes to infinity of the ratio of successive terms, so 1 by n plus 1 divided by 1 by n, this is equal to limit as n goes to infinity of n by n plus 1, which is equal to 1. And we know the series diverges. Beforehand itself, we know series diverges. This is just to show you how the limit, what the limit is. Now let's look at the series 1 by n square. So if we take the limit, we again end up with 1. And we know the series converges. Now let's look at this series 1 by n times natural log of n. So again, if we take the limit as n goes to infinity, keep simplifying this, we again get 1. How did we get this? Because 1 plus 1 by n, when we take the limit, it goes to 1. And natural log of 1 is 0. So this term becomes 0. And the limit of the remaining ones is 1. Okay. Now again, if we look at this series, 1 by n times square of natural log of n. Again, if we take the limit, we again get 1. And we know the series converges. So in all the cases, the limit of the ratio of successive terms u sub n plus 1 by u sub n is 1. Yet the series exhibit different convergence behavior. Some were convergent, some were divergent, but all their limits of ratio of successive terms was 1. So L is equal to 1. When we end up with this situation, the ratio test is inconclusive. So now let's actually solve a concrete example. Is this series 3 to the power of n divided by n factorial convergent? So general term is 3 to the power of n by n factorial. So we take the ratio u sub n plus 1 by u sub n, which is equal to 3 to the power of n plus 1 divided by n plus 1 factorial divided by 3 to the power of n by n factorial. Okay, now multiplying it with its reciprocal, we get 3 to the power of n plus 1 by n plus 1 factorial times n factorial by 3 to the power of n. We split 3 to the power of n plus 1 as 3 to the power of n times 3 times n factorial, and we split this n plus 1 factorial as n plus 1 times n factorial times 3 to the power of n. So 3 to the power of n, 3 to the power of n cancels, n factorial cancels, and we are left with 3 by n plus 1. And if we take the limit, we end up with 0. So if it is 0, it means it is less than 1. So the series 3 to the power of n by n factorial is convergent by ratio test. So that was comparison test 3, or the ratio test, or the D'Alembert ratio test. Now, if you found this session helpful, please do like, share, and subscribe. Comments and suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.